Good afternoon.
Good afternoon.
Our last lecture of this. Yes, questions? So our last lecture of this week. And then we had a weekend. That's always nice to have if you don't have other work to do. And so today, first of all, we will have a very quick reminder of what we did last time, and then we will see what we see. So today we should finish up with the ellipse and maybe, just maybe, start with the hyperbola. And so what we did, go to the, come back. Oh, it's there. All right. So we introduced the conic sections. So first of all, the second order curves, that is, because the equation involves a second order polynomial containing two variables x and y. The conic sections, they are called conic sections because they're basically the shapes can be obtained by cutting a cone with a plane, so finding the intersection of a cone and a plane. So those shapes would work very, very well and will be perfect, and they have interesting geometric properties. As we already saw, some geometric properties develops. As for the circle is familiar from school, and you of course remember very well that the locus of all points in the plane, equidistant from a given point, is a circle. In other words, the circle is the figure in the plane that is formed by all those points that are at the same distance from some given point. And of course, this given point is called the center, and the distance is the radius, and the equation is this. So this is what we considered last time. That's what we looked at on Wednesday, and we solved quite a few questions about circle, quite a few practice exercises, and I actually promised to keep 2 more exercises for today. At the moment, I decided not to add more exercises about the circle because we really need to get on with the material. Next week, Monday and probably part of Wednesday, we will actually solve a lot of examples, have a look at the several exercises, all about circles, ellipses, lines, hyperbolas, parabolas, all that is necessary. And so we had these exercises, some of them, but the last two, I guess, were some things that remain not finished. So let's do these at the moment now. And then we move on to ellipse. We didn't do many exercises. Actually, we didn't do any exercises. But we didn't manage to do ellipse altogether. Alright, I am going to switch off the camera now. And so, a circle is tangent to two parallel lines. And, okay, the lines are given, and one of the tangency points, one of the points of tangency is given. So what we have is evidently a circle. Okay, this will look very much like a circle, but more or less. More or less a circle. So we have two lines tangent to the circle. All right, I will pretend that this is one of the lines tangent to the circle. If the two lines are parallel, that means the other line is exactly on the opposite side of the circle. So points of tangency, 2 points of tangency. One of these points is A with coordinates 2, 1. Unfortunately, at this moment, I don't exactly know yet on which line it lies. So which is which line? And of course, we understand that the points of tangency, because from the center, if I draw the radius to the tangency point, and then the other one to the other tangency point, I actually get the diameter. Why is that? Because remember, we had the radius drawn to the tangency point is always perpendicular to the tangent point, and that's at both ends, which means basically the two radii actually form the diameter. And we have the center C, for which we don't know the coordinates. But we know the two equations for lines. They are parallel because we can see, all right, this is supposed to be minus or plus. Let me think, but it was supposed to be minus or plus. Oh, it doesn't matter. Let's make it plus. That's the only reason why I could evidently put a plus, an equality sign, because I was trying to type a plus and accidentally pressed shift, I guess. It was plus. Well, if it's not plus, if it's minus, there will not be much difference except with the numbers, of course. So, now, we write the equation of the circle, but first of all, we have to understand on which line this point A is. If I put, now we have a slight problem here. Actually, I have long been intending to rework this problem because we have a problem like this. See, the normal vector of this line is 2, 1. Normal vector. The normal vector of that other line is also 2, 1. It's the same normal vector, but at the same time, the point A has also coordinates 2, 1. These have nothing in common. This has nothing to do one with the other case. Normal vector is normal vector. That actually would be the vector in the direction of this diameter, because it has to be perpendicular to those both lines. But the point has coordinates 2, 1. That has a completely different idea. So first of all, let's put the point A. Put point A into the first line. We see 2 times 2 plus 1, which is y value minus 5 equals 0. We see that this is evidently the line 1. That is with equation 2x plus 1 minus 5 equals 0. And the other line will be L2, the second line, with the same normal vector 2x plus 1, but plus 15 in this case. Okay, I didn't have to use that parentheses. That's not the parentheses. They are not supposed to be there. Equals 0, of course. Equals 0. So we know the point A, we know which line is which. And now the interesting thing is, of course, how to find the center of the coordinates. Or the second question is, how do we find the coordinates of the second point? If we have the coordinates of both points of tangency, then we can in fact find the midpoint of the segment AB. That would be the center C, and we can also find the radius. Another possibility, if I simply find the distance from A to the line L2, to the second line here, if I can find this distance, then I know that's going to be the half of that distance is going to be the radius. So in fact, I can do it quite quickly. So I can find that radius because, as we already saw, as I said, the radius is perpendicular to the tangent line if it is drawn to the point of tangency, which means both of them that we need in this question are actually forming the diameter, and we can find quite a few things. So if we could only find the coordinates on the point B, so perhaps that might be the first thing we need, because without the point B, it is possible to get the radius, but it is possible to get the center, but that would be too messy. So let's try to find the point B, which means we need to write down the equation of the line AB. We know the point A, and we actually know the direction vector of the line AB. The direction vector of the line AB is the same as the normal vector of the line 1, because we see how the normal vector, of course, is perpendicular to that line L1, which means it's parallel to our diameter. This is the reason why we actually do need a sketch always. In all these tasks of analytical geometry, it is important that we sketch so that we have an idea. So the direction of this line that we are trying to draw, I will actually, okay, no, that, I will actually try to involve some color perhaps. So maybe a little bit of green, maybe a little bit of green. I am right now writing the equation for this line. So for this line, we have a point, we have the normal vector, which is actually already known. Let's simply write it down. And the normal vector is 2, 1. And so this becomes the direction vector of the green line AB. So the equation of AB would be, remember, x minus 2 divided by 2 equals y minus 1 divided by 1. To remind you how things work out with this. So let's
Miss, can you tell what is N1 again? The N1. The
N1,
vector N1.
normal vector of the first
Okay.
line.
Okay.
N is always a normal vector, and then 1, in this case, the first line. However, of course, we understand that for the second line, the normal vector is the same. That should be understood, of course. And so, let's see, 2 and 1. This is the normal vector. This is where 2 and 1 come from. This is the normal vector. Coordinates 2, 1. For the second line, because it's parallel, 1. So if it was y1, it was supposed to be y. Okay, sorry, I was thinking how I was going to work this out. So this is y, of course, and this is y, but that's 1 y, evidently. So the 1 comes from there. And so I go back to the highlighter, and I see that the normal vector coordinates are these. The vector coordinates are these. However, because by coincidence, it's not on purpose, by coincidence, let me see, let's say something, that's orange. By coincidence, the coordinates of the point A have exactly the same number. The same number. So this is 2 and this is 1, and they come from the vector, they come from the coordinates from the point A. So in fact, I have to do all this coloring simply because I usually forget that I have to change some numbers in this task so that we don't really get all the same numbers all the time. So in this case, let me remind you that 2 and 1 and 2 and 1 are coincidental. So this would be 1. And I will just put 1 times 1 where we were checking this. So again, just to make sure that we understand what is going on. So these are the coordinates of the point A, and then we can come back. And then we can have and then the coefficients of the line. So that you understand that these are, in principle, those are different numbers. The 2 and the 2 are not the same. So the yellow 2 and the yellow 2, yes, and the pink or orange 2, yes, but the two 2's are not supposed to be the same numbers. They could be different numbers. All right, so now we have the equation of this line AB. And for that, we have to simplify it so that we can find its intersection, point B. So how to find point B? Point B is the intersection between the line AB, intersection, and line L2. Which means I have these two equations. I have the equations now. I will cross multiply to make things simpler. I will have 1 times x minus 2 equals 2y minus 2. That's from multiplication here. And from L2, so this was AB, and the line L2 will be 2x plus y plus 15 equals 0. Or I can write x minus 2y equals 0 and 2x plus y equals minus 3. And so we have a system of equation. If we solve it, for example, if I multiply the first equation by minus 2 and that to the second equation, I get 5y equals minus 15, y equals minus 3, and then x is 2y, that's minus 6. So those would be the coordinates of the point B. So this means that the point B has coordinates minus 6, 3, minus 6, 3. And now I can actually find the coordinates of the center then. So the coordinates of the center would be, take the average values of the coordinates A and B. So x coordinate of A plus x coordinate of B divided by 2, and y coordinate of A plus y coordinate of B divided by 2. So the coordinates of the point C is minus 4 divided by 2, negative 2, and 4 over 2 is positive. So this is the center of the circle, understanding that it is, of course, the midpoint of that diameter AB. The midpoint of the diameter AB. We used coordinates of A and of B. And then when we have the center, we need to find the radius. We can find it in two different ways. One is find distance from A to line L2 and take half of it. Or the other one is simply take the vector AC and its length. In this case, not a problem. So the vector AC would be C coordinates minus A coordinates, minus 2 is minus 4, and C2 minus 1, 2 minus 1 is 1 again. So this is the vector AC. So the radius is, of course, the length of this vector AC. That's 16 plus 1, the square root of 17 in this case, which means for the formula, now for the equation, finally, for the equation, we now see that we have x minus x coordinate of center, that would be x plus 2, squared, plus y minus y coordinate of the center, that is 2, squared, equals
Professor,
radius squared, that's 17. Yes?
I think the y value is minus 3, and I will show you.
Wait, where?
Yes.
I think point C, x coordinate should be 2 plus 6 divided by 2.
2 plus 6, y plus.
Professor, this value.
We add the coordinates of the endpoints, one endpoint plus the other endpoint, divided by 2. That's the midpoint.
Okay.
Those would be the midpoint coordinates, because y1 plus y2 divided by 2. So if we have the coordinates of A and B, these are the coordinates of midpoint.
Yeah,
It's not a vector. It's not a vector. You do not subtract.
Mm.
Okay, something is happening in my brain that at times wants to act up. Let's see how, if it's serious. And therefore the center has coordinates minus 3, 2. And of course the radius is square root of 17. So this means that here we have square root of 17 squared. So 17 is radius squared. The radius itself is square root of 17. So we can see that if we found the distance from A to the line L2, it would not be a very nice number. It would not be perhaps a very nice number then. So it would be square root of 68, and then we would have to transform it in order to get the radius. So evidently the vector coordinates in this case were easier. So let's just, I'll put some numbers on this simply to remind you in what order we did these things. So we started with this. That was the first thing we did. We wrote the equation for the line AB. Secondly, we found the intersection point of the line AB and the line L2. That is, we found the point B. So point B has coordinates -6, -3. Then the third thing is we find the midpoint. We find the midpoint that was here. We find the midpoint, which is the center, and the center is there. And then number 4, we find the vector that is the radius of the circle and its length. And finally, number 5, we write down the equation. We can write down the equation. All right. So this involves. This is not a simple question. It does seem simple to me, but because I'm doing it every year, every semester at this point, anyway, it's very clear to me what you should do. But in principle, yes, you have to have a sketch. It doesn't have to be in coordinates. It can be just a sketch, circle, and 2 parallel tangent lines. It doesn't matter where the points are actually. And you'll need to have some geometrical ideas. So remember that in this case, we have to understand that AB would be the diameter, the segment connecting the 2 points of tangency, and that the center is the midpoint of the diameter. As we remember this, and the perpendicularity, then we can proceed with the solution. But the first thing really was to sketch to understand what is going on here. And yes, the somewhat unpleasant coordinates of the point, coordinates of the number of the normal vector, which need to be distinguished so that you understand what is going on. So ideally, they should have been all numbers different, so that we could see what comes from where. I just used some coloring. All right. Then we have center on the x-axis, and the circle actually itself is passing through these 2 points. 0 minus 2 square root of 5, that would be the point on the y-axis, and 6 4 roots of 2 is the coordinate, is the point somewhere. So we could think, I'm not actually saying that this is the accurate picture, but the thing that I might imagine could be center somewhere on the x-axis, but we don't know exactly where. It could be on the negative x-axis for all we know. Before we have started actually calculations, we have no idea. So it passes through the point somewhere on the negative y-axis, as we can see somewhere. And it also passes through, that would be point B. And it also passes through some point in the first quadrant. Somewhere there. So we might actually imagine that we have a circle, something like this. So the point somewhere in the first quadrant, okay, let's suppose that this is the point here. And now they are not necessarily the opposite sides of the diameter. They are not, well, actually not necessarily, but they are not. However, we know point A, we know point B, and we know that the center is on the x-axis. So what do we do? How do we find the equation? Well, the thing is, then that we actually don't know, but we know that the center has coordinates, let's say x.
Yes. Yes, but they say 0 x-axis, right? So the point supposed to be on the y-axis because 0 x-axis will be on the y-axis.
Yes, that's the point B. 0 minus 2 square roots of 5 is this point.
No, miss. The question says write the
The
equation of the
center is on
circle.
the x-axis. If the center is on the x-axis somewhere, it means the x-coordinate is something, but the y-coordinate we know is 0, because on the x-axis the y-coordinate is 0.
Because it says 0 x-axis. That's why.
With the
Okay.
center, write the equation of the circle with center on x-axis. Center on
Okay.
x-axis, that's this point C. At this
Okay,
point,
okay.
x value is something that we don't know, that's x0, and the y-coordinate is definitely 0 because we are on the x-axis.
Axis. Okay, okay.
And so now we don't know x0 and we don't know the radius, unfortunately. So at this moment, I have to write that we have x minus x0, which we don't know, squared, plus y minus 0. So that's simply y squared because the second coordinate of the center is 0, and it equals radius squared, which we do not know. So there's a lot that we don't know. The one thing we do know at the moment, for now, the one thing we do know is this y squared. It doesn't have y minus y0 because y0 is actually 0. Because of this, we know that we have plain y. Now, let's simply put in some values. So supposing that point A means this, so 6 minus x0 squared, the center, 6 is the point 6, this is x, this is y on the circle. So I'm putting 6 minus x0, which I don't know, plus y squared, that is 4 roots of 2, square equals radius square. Unfortunately, I can't do better with 1 point. And from point, this is from point A. This is from point A, or 4 point A. Now for B, let's put the coordinates of B. So 0 minus x0 squared plus y squared. Okay, sorry. Have to waste some time. This. So we have y squared. Y squared would be minus 2 square roots of 5 squared equals radius squared. In fact, now I have a system which does not look nice at all unless we simplify. So what we did was, first of all, we understand that because we have this 0 on the x-axis, we have y equals 0 for the center, we don't need anything here. We don't need to write y minus y0. That's the first thing. This is the general equation then. This would be the general equation of the circle, in principle, in general, without knowing much else. So we put the coordinates of A into this equation, and we put coordinates of the point B into this equation. So now what we can do is simplify these. We have 36 minus 12x0 plus x0 squared. Now we have 4 square roots of 2 squared will be 16 times 2 equals radius squared. And on the other side, we have x0 squared plus 4 times 5, that is this number squared, equals radius squared. So at this moment, we see that in both cases, it has to be r squared, which is the same. The right-hand side is the same, which means that we can simply take and rewrite it as a single equation. If the radius squared is the same in both cases, I can simply equate both sides. So I can simply write x0 squared minus 12x0, and then we have these. 32 plus 36 is 68. 32 plus 36 is 68. Has to be equal to x squared plus just 20. And now x0 squared is the center point. So now we see that x squared and x squared on both sides can be cancelled out. They won't matter really. So cancel out and cancel out. And what we have now, again, that is minus 12x0 equals 20 minus 68, sorry, because the result will be 48 minus 48. So I have minus 12x0 is minus 48, and x0 is 4. So this point actually turns out to be 4 on the x-axis where the center is. And now, if x0 is 4, then from the second equation, I can say that 4 squared plus 4 times 5 is actually radius squared. So that would be 16 plus 12, would be 16 plus 20, that is 36. So radius squared is 36, or I can say that the radius is 6. And so I can finally write the finalized equation of the circle, and it would be x minus 4, because x0 was 4, plus y squared equals radius squared, which is 36. And it means that we have the center at 4, 0, and the radius equal to 6. So again, a lot of combination. So as you see in analytic geometry, we combine geometrical ideas which we can look at in a sketch. So we must draw a diagram, we must make a sketch to understand the geometrical connections. And then there are some formulas, not so many formulas from analytic geometry as such. And then we can basically we solve equations and work algebra. We solve equations and we work algebra. So the equation, the answer is. So we start from geometry. We put in numbers into the unfinished equation, which still has unknown constants. Then we solve a system or an equation to find those unknown constants. And yes, then you can write down the equation as it is. And now, so that was let's say finishing up with circle. Now let's go on to the ellipse. And the ellipse, remember we had this definition, the locus of all points for which the sum of the distances, the two given points is constant, and the canonical equation is obtained if we simply decide, now I'm going to do this, to put both the foci, those 2 points, on the x-axis at equal distances from their original coordinates. Then we get this canonical equation. This means that this only works for the ellipse whose foci are on the x-axis, or the ellipse that is symmetrical with respect to the origin. So such ellipse is placed very carefully. Of course, in principle, I could have an ellipse there. I even can have an ellipse like this in a skewed way. But to get the canonical equation, we deliberately do this. We decide to put this ellipse in the system of coordinates like this. And then we can see that the minor, we have the semi-major axis, the half of the greater half axis. Remember that 2a was the total length of this ellipse, and yes, that distance, that sum of the two distances from any point of the ellipse to the 2 foci is actually, yes, equal to 2a. We saw that last time with that little animation. And now we just remember that if the length is 2a, that means the intersection points on the x-axis are A and minus A. And similarly, the intersection points on the y-axis are B and minus B. And the 2B, this distance, the smaller radius, the distance, is called the minor axis. And B is half. B is half of this minor axis, so we call it the semi-minor axis, or the smaller, the lesser half axis. So altogether, we can imagine that the ellipse is actually inside some rectangular frame in a box. Inside a rectangular box with size 2a by 2b, of course. And then we see that if we denote the coordinates on the x-axis of the foci C and minus C, then we see a formula. Well, we don't see, but it can be done. The formula can be found. C squared equals A squared minus B squared. This can be proved. It's not even too difficult to prove, but we will skip that part. As long as you try to remember this, or you can find it in the formula sheet, evidently. What else is there? The eccentricity. Remember, we have a thing called eccentricity. Eccentricity is the ratio of the focal distance from the center to the major half axis, the semi-major axis. So eccentricity can be found if we know the focus coordinates of at least one focus, and we know the major axis, or rather the major half axis. In principle, the greater this is, the closer this is to 1, if it approaches 1, then we can say the ellipse is long and thin, comparatively long and thin. It's the shape. And if it approaches 0, then it is short and fat, more like a circle. Short and fat, more like a circle. The circle has eccentricity 0, which means we could say that the circle is an ellipse whose foci are in the center. So 0 eccentricity. Eccentricity, in fact, is a measure of comparatively how far each focus is out of center. So how far off center each focus is. This all works with the assumption. That A is greater than B. Basically, this means the ellipse is placed horizontally, the horizontal ellipse. This ellipse is placed horizontally. Now, of course, we could say sometimes it is more convenient, who knows for what reason, for what purpose, but it might be convenient to place the ellipse vertically. That is, we still call the intersection with the y-axis B. This does not become A. We still call the intersection point with the x-axis A, but in that case, in this case, simply B is greater than A. If B is greater than A, or A is less than B, in that case, we see that the foci are on the y-axis. The foci are on the y-axis then. And in this case, the equation is still the same. So how do we know? We simply compare the numbers A and B. I can have an equation x squared over A squared plus y squared over B squared equals 1. When I look at this equation, I recognize which is the greater number, A or B. If A is greater, then the ellipse is horizontal. If B is greater, then the ellipse is vertical. And of course, the foci are placed accordingly, looking at this elongation of the ellipse. So A now is the semi-minor axis, the smaller axis, because it's the shorter one. And B is now the semi-major axis, being the longer one. C, still the coordinates of the foci, but in this case, the foci are on the y-axis. So the coordinates are not C0 and minus C0, but rather 0C, 0 minus C. They are on the y-axis. Again, symmetrical with respect to the origin. And yes, sometimes the ellipse might travel about. Sometimes the ellipse might be shifted somewhere else. In that case, we will actually pretend, well, we not pretend, but we will do the same thing that we do with the circle that is not centered at the origin. Okay, the formula c squared is now not a square minus b squared, but b squared minus a squared. We have to look at which is the greater number, b or a. For the horizontal ellipse, a is greater than b, so it is a squared minus b squared. For the vertical ellipse, b is greater than a, so it's b squared minus a squared, of course. And eccentricity is measured now against b, c over b, because b is now the semi-major axis. It's always the distance of focus from the center, divided by major half axis, semi-major or radial half axis. So in the horizontal case, it was c over a. In the vertical case, it's c over b. So these very small but important details, which basically depend on if you see the equation of this ellipse, then you are able to figure out what it looks like, how it is placed vertically, horizontally, and so on. And now, yes, there we go. Some exercises. So we are starting with a situation where the foci of an ellipse are on the x-axis. In other words, in this exercise, in this part, we will consider the ellipse that is, doesn't look very good, but meaning this one, horizontal ellipse, because the foci are on the x-axis. And symmetrical about the origin means, okay, we have this situation. 1, 2, F1, F2. And now and this is A, of course, and this is B, the numbers, and this is minus C, and this is C. And let's see how we can write the equation. Distance between foci is 30. Okay, the distance between the foci is evidently 2C. 2C is 30, and the major axis, that is 2A, the full, not half, is 34, which means C is 15 and A is 17. So to write the equation, we need B. To write the equation, we need B. Let's just remember that C squared is A squared minus B squared. So that would be 15 squared equals 17 squared minus B squared. From there, you can find B squared is 17 squared minus 15 squared, which is 8 squared, 64. If you have a difference, then remember you can actually make the calculations very simple by applying the formula 17 plus 15 times 17 minus 15, which would be 32 times 2, which would be 64. So B is actually 8. Or for the equation we need 64 anyway. And so the equation for this ellipse, write it in something, a nicer color. Okay. So we have x squared divided by a squared. A is 17. So I can write 289 because that's 17 squared, plus y squared divided by b squared. B is 8, b squared is 64, equals 1. And there you go, we have the equation. We used a value 17, so the square is 289, and we use b value 18, or we already see that b squared is 64. And that is the equation of an ellipse with these properties. The equation of an ellipse with these properties. we can actually imagine that this is a comparatively long, thin, long and narrow ellipse, because see, A is 17 and B is 8. Basically, B is less than half of A. So, well, not extremely long, but at least longish. So the ratio of size is probably the width to length is approximately 1 to 2, or a little bit less. Next, eccentricity is 2/3, and one focus is at 6, 0. So this is a new case. This is a new situation, which means that evidently C is 6. From this we can say that evidently C is 6. Eccentricity, 2/3. Remember that eccentricity is C divided by A. Does that mean that A is 3 and C is 2? Not really. So this is very important, and in this place, this is a very common mistake that people get confused. Okay, eccentricity is C divided by A, so if it's 2/3, it means C is 2, A is 3. No, actually no, it's only the ratio. The ratio after simplifying is 2/3, no problem, but that does not mean that C is exactly 2 and A is exactly 3. We actually know that C is 6 and A is something that we don't know. So in fact, we have eccentricity is distance of focus from origin divided by major half axis. So 2/3 is 6 divided by A. And from this equation, we can find A. From this equation, from eccentricity, we find A. It's not that A is 3, because C is not 2. So let's just remember that eccentricity, it might be a fraction, but it is after simplifying. After simplifying, it's only, it's not the actual coordinates, not the actual segment length. So we see 2A is 18 and A is 9. Okay, we have A. Now to write the equation, we also need B. Okay, C squared equals A squared minus B squared. We can simply put in the numbers. C is 6. All right, 36 equals A squared, that is 81, minus B squared. This is simple to find. B squared is evidently 81 minus 36 is 45. So that's B squared. And then we can write the equation x squared divided by A squared. A squared we already have there, it's 81, minus y squared divided by b squared, but we see b squared is 45 equals 1. And that's it. That's the equation of this particular. So, okay, I forgot to write some nice color, so at the moment I will simply try to circle it in some nice color. And so these are the two solutions. So writing canonical equation means, of course, write the equation in the form x squared over a squared plus y squared over b squared equals 1, the canonical form. What those numbers are, we can find from the conditions that are given in the tasks. All right. Let's see if I had something else. Yes, I have D as well. All right. Now a different type of problem, because here we have only the semi-major axis, that is, we only have the value of A. We only have A. See, semi-major, okay, without 2. So A is 4. We don't know B. but we have to write the equation. So again, because we know one point, we can in fact again do the same thing that we did before. I write the general equation, canonical x squared divided by 16 evidently plus y squared divided by b squared, which I don't know, and it is equal. And now I see from this point, we can take x is minus 2 and y is 3 square root of 3 divided by 2. And put that point, the coordinates of that point, into the equation. Then the only unknown number will be b squared. And we can find it. So we have x squared, that would be 2 squared. Okay, if you like, you can write minus 2 squared. Just remember the square will be positive, divided by 16. Plus now y squared. Okay, it will be 3 squared is 9, plus root of 3 squared is 3, divided by 2 squared is 4, and all of that divided by b squared should be 1. So in principle, we could, for example, well, we could do many different things, but let's have a look at this. 4 over 16 is 1/4, plus 27 over 4, that's this value, and dividing by b squared means I have to write b squared below, because I am dividing not by a fraction, I'm dividing by an integer. Remember that if we divide by integer, this integer goes below the line. Equals 1. So in this case, not so hard to see. So 27 divided by 4b squared equals 1 minus 1/4 is 3 over 4. Multiply both sides by 3, for example. By 4. If I simply multiply both sides by 4, I get 27 divided by b squared equals 3. That's simple. That means b squared is 9. And so we can write the equation. X squared divided by 16, because a squared is 16, plus y squared divided by b squared, which is just solid 9, equals 1. So we can find the missing constants, just like with the circle, if we put the coordinates of a point on that ellipse or on that circle into the unfinished equation. That would be this one, unfinished equation. So if we know a point and we can put the coordinates instead of x and y, then from there we can of course find the missing constant. In this case, b squared. That was okay. That's for B1. This is the ellipse where the foci are on the x-axis. Now the next question is, what about the ellipse where the foci are on the y-axis? So first of all, it would be good to have an idea. It would be good to have a sketch. Again, figure out how not very realistic. Okay, so the foci are on the y-axis, but it's still A on the x-axis, it's still on the y-axis, the intersection point. And now, minor axis. Minor axis means the total axis, that's 2A. It's still 2A, although now it's not major, it's minor. But because it's horizontal, it's 2A. So 2A is 16, which means A is 8. Eccentricity, epsilon, is 3 over 5, but the eccentricity is focus coordinate C divided by, in this case, it will be B. In this case, it's B, because the ellipse is the vertical variation. We have the vertical ellipse. So this is a little bit problematic again, because we do not have C, we do not have B, and it would be a mistake to say, okay, I guess B must be 3 and B must be 4. Not true, by the way. B has to be greater than A. So we have to think. We have two things now, two kinds of information. The first information is that CB is 3/5. That's the eccentricity. And then we also have that C squared equals B squared minus A squared. That was from the ABC relation, ABC connection. C squared will be, A squared will be, as we know, 64 because A is A. So in fact, I would say that C is 3/5 times B. I can express C using B. And here I have C squared equals B squared minus 64. Okay, so I could probably take this expression from the first equation and simply put it into the second equation. I can take this and put it instead of C to solve some kind of equation, just to understand what is going on there. So this cannot be solved more in a simpler way. This does not work simply. As you see, it's a bit complicated. We have to find the connections, and then we have to realize that we still have two terms, two numbers unknown, and in principle we need to get B in order to write down the canonical equation. And so 3B/5, that's C squared, equals B squared minus 64. Or I can say it's 9B squared over 25 equals B squared minus 64. One thing you can do is perhaps you could multiply both sides by 25. Would not be a problem. Or bring, because on the left-hand side we have less than B squared, the coefficient is less than 1, we could actually move it to the right-hand side, subtract 64 moves to the left, and so on. Or we could simply multiply both sides by 25. Anyway, what we have to do, we understand, what we have to do is we need to solve this equation. As soon as we solve the equation, B squared, we can write down the equation. X. I don't really need B, I need B squared. Remember that the equation of the ellipse is still the same. X squared over A squared plus Y squared over B squared. And so if I, for example, multiply everything by 25, I would get 9B squared equals 25B squared minus 25 times 64. I'm too lazy to multiply really. Now I bring this to one side and that to the other side. So I have 25 times 64, I'm still lazy. 25B squared minus 9B squared is 16B squared. Now, see, it sometimes pays to be lazy. I can divide both sides. I can divide both sides by 16. So divide by 16, divide by 16, you get 4. So B squared is 100. So a little trick, and I don't need B really, because all I need is the equation. So I have A squared, I have B squared, so I can write the equation now. X squared divided by A squared, A is 8. So x squared divided by 64 plus y squared divided by b squared, and b squared is 100 equals 1. That's it. That's the equation. Now we see clearly that b squared is greater than a squared. That is, b is greater than a. That is, the ellipse is indeed, it has to be vertical. It has to be vertical. If we want to find the c coordinates, we could, but we could find the c coordinates even from here. If b is 10, then c is 6. that makes sense if we need to do this. At the moment, that was not required. We could actually make this ellipse. We could write the equation of this ellipse, and everything works out just fine. So basically, as you see, half of the solution is understanding the condition. If you understand correctly what is given, then, well, this is still stating what is given. That's already half of the solution, because the rest is a little bit of algebra. You are supposed to understand algebra. So, understanding what is what number is what number, we actually already are on, well on our way to complete solution. So, in principle, it's not worth hurrying or doing other things when you see a new question, a new problem. The first thing to understand is, do I understand what is given in this task? And if I do, then I can start writing down the conditions mathematically, and then I can start combining them and solving them. Basically, in geometry, the solution will be from algebra. The understanding of what to do comes from geometry, but the solution itself is from algebra. We solve the system of equations. Another one. Locus of all. I have. All right, it didn't copy. I'm very sorry. It didn't copy the coordinates of the points from and. Yes. So there were 2 points. There were 2 points whose coordinates I have now lost, it seems. I'm sorry. Let's say that these points are, for example, -2, 0, and 2, 0. So these points on the x-axis. I'm now imagining. Now it's simply something that I have lost. But let's suppose the points are these: -2, 0, and 2, 0. So evidently, remember that locus of all points whose sum of the distances, that is the ellipse. That is the ellipse. And the 2 points given are actually the foci of the ellipse. But 2, 0 is there, -2, 0 is there, -2, 2, and the locus of all points whose sum of the distances is 8, that would mean, remember the sum of these two, mf1 plus mf2, if m is the point in general, xy is the point in general, the sum had to be equal to 2a, that is for k. It is major axis. So in fact this means that the major axis should be 8, which means the major half axis. So if this has to be 8, this means that a, the major half axis, is 4. There and there, so there would be something like this. Sorry, the shape is awful, but that's what happens if you draw with the mouse. All right. So now we have evidently we have 2 and minus 2, so C is 2. We have, in this case, B is smaller than A. This is a horizontal ellipse because the points I gave are the horizontal points. And that means that I can find the value of B squared. So remember that C squared is A squared minus B squared. So that be, let's see if I can have this. I think it might be impossible. No, why not? 16 minus something equals 4. Yes, of course. So C is, as we know, 2. So 2 squared is 4 square minus b square. So b square would be 4 square minus 2 square, that's 16. Minus 4, that's 12. That's 12. So we can write the equation x squared over 16 plus y squared over 12 equals 1. That's all there is. So in principle, if these points have other numbers, not 2 and minus 2, but perhaps 3 minus 3, or maybe 2 square roots of 2 minus 2 square roots of 2. You can still use these as C. You can still use them in the equation. Maybe you might have got different numbers, but in the end, the only problem would be if I had put C value greater than the A value. That shouldn't be. C cannot be greater than A. Focus cannot be outside the ellipse. Apart from that, this is simply thinking through the equation, understanding what the numbers in the equation mean, A, B, and then remembering those numbers C and the eccentricity. They also could appear. All right, find everything that is necessary. Let me check the time. It's 23 minutes. Good. So find the semi-axis, foci, eccentricity. Sometimes you might be required also to sketch it approximately. So how do we approach this? How do we even know that this is an ellipse? If we move 225 to the right-hand side, remember that the ellipse needs 1 on the right-hand side. So I can think 2x squared plus 25y squared equals 225. Now, if I divide both sides by 225, simply to get 1, that's how I do it. Divide by 225. So I have 9x squared over 225 plus 25y squared divided by 225. In fact, 225 is 9 times 25. So I have x squared divided by 25 plus y squared divided by 9 equals 1. We simply move the constant to the right-hand side, divide everything by that constant so that we have x squared divided by number, y squared divided by number, and on the right-hand side, just the number 1. And so we can see that this is a squared. Because a squared is 25, then that means that a is 5. Because b squared is 3, b squared is 9, sorry. It means b is 3. This means that the ellipse is horizontal. We have 5 minus 5, 3 minus 3. And to find foci, the foci will be on the x-axis. And so c squared equals a squared minus b squared. That is 25 minus 9, and that is 16. So the foci are, one focus is at the point minus 4, 0, and the other focus is at the point 4, 0. And what else? Oh, the eccentricity. And then eccentricity is focal distance, that is 4, divided by major half axis, which is 5. And that's it. So we simplify, we rearrange this equation so that we get the canonical form, so that we actually have this canonical form, because from the canonical form, we can immediately get A and B, the half axis, the semi-axis of the ellipse. If we get those, we understand horizontal or vertical, we understand what happens to the foci, and then we can just find the foci. And as soon as we have C and A and B, we just write the eccentricity. That was A. B is something similar but slightly different. Why? If we divide now both sides by 45, we have x squared divided by 5 plus y squared divided by 9 equals 1. That is after division by 45. So this means that the half-axis A is square root of 5, half-axis B is 3, but from the squares we see that B is greater than A. That means that this ellipse is the vertical kind. So the foci will be on the y-axis. And so I have a squared is 5, b squared is 9. So c squared is b squared minus a squared because it's vertical, the vertical variation. So 9 minus 5 is 4. And focal distance would be 2. We don't write plus or minus 2. We assume that ABC constants are always just positive. In the coordinates, we might get negative coordinates, but the constants themselves, as constants, they will always be positive. So, all right. So the foci will be 0, 2, the upper one, and the lower one would be 0, minus 2. And the eccentricity is C over B, in this case, vertical kind, C over B. So C is 2 and B is 3, and then we have the eccentricity. I will separate these cases. This was the whole thing. That over there was the first case. This is the second case. Second question. And finally, D, 25x squared plus 9y squared is 1. The problem is that we already have 1. So we don't divide anything by anything anymore. We cannot divide both sides by something because we already have 1 on the right hand side. So we have to understand that x squared is divided by 1/25. That y squared is evidently divided by 1/9. Remember, when you divide by a fraction, it gets turned upside down. And so we see that A is 1/5, and so that B is 1/3. So half axis, which means this is again the vertical kind, because 1/3 is greater than 1/5. Unlike what it looked at the beginning, it was in the wrong form. We had to get rid of the factors. We had to write it using ratios, quotients. And so, all right, c squared equals, because this is vertical, it has to be b squared minus a squared. That would be 1/9 minus 1/25. And that would be 9 times 25, 25 minus 9, that's 16 over 225, which means C value is 4 over 15, taking the square root. And it's on the y-axis. The foci are on the y-axis. So for this, what I have to think of is that the foci F1 is at 0, 4 over 15, and the second focus will be at 0 and minus 4 over 15, because we took square root of c squared. And eccentricity would be c over b, because it's, again, this is the vertical kind, so this is vertical. The first one was horizontal, and this is again vertical. C over b, that would be 4 divided by 15, and divided by b means divide by 1 multiplied by 3. So it is 4 over 5. See, the eccentricity is exactly the same. The shape of of these two ellipses is the same, but the size differs and the location differs. So eccentricity the same simply means the proportion, the ratio of length to width is the same. But of course the value, the size itself is different and the location itself is also different. Remember that the eccentricity basically tells us whether the ellipse, how thin comparatively is the ellipse. Is it short and fat? Is it very long and thin? The ratio, this ratio is determined by the eccentricity. How much time do we have? Oh, we have some time. Okay, it looks like we will not have time to go into hyperbola today. Oh no, yes we have. We have time to go into the hyperbola. What I am missing here, and we will discuss those questions, those problems next time probably, is the situation when the ellipse is not at the center of the coordinates, but it's moved somewhere else. It's moving away. So that situation will be discussed a little bit later. For now, I would say the basic ideas, the standard situations are more important than trying to shift the ellipse somewhere else. Now we have this. Some minutes, all right, let's go a little bit into the hyperbola. A little bit into hyperbola. We will not have time enough to finish it. Again, only probably one version of hyperbola. And the hyperbola definition is again interesting. Remember our...
Miss.
Yes.
Miss.
Yes.
Miss, what's the difference between a first order curve and a second order curve?
First order curve is not a curve at all. First order curve is x, some number a times x plus some number b times y equals some number c. It's a line. First order means like first order equations, first order polynomials. It's linear. This would be a line. But as soon as we have some squares or products or something like this, then we have one of these curves that are circle, ellipse, hyperbola, parabola. That's the difference. If we only have first order terms, then it's a line. It's not a curve at all. So this is a curve.
Okay.
This is the line.
Okay,
But in this case, when we are talking second order curves, we really need curves because the equation will involve squares or product of the two variables, so second order terms. As soon as it involves second order terms, it's one of the second order curves that we are discussing. It is possible to demonstrate that there's no other options, no other possibilities actually than hyperbola, parabola, circle, and ellipse. Only these types of second order curves exist. Any equation of second order will give you a hyperbola, parabola, or ellipse, or circle. Now hyperbolas. So definition is, in a way, it's very similar to the definition of a parabola, of an ellipse. And that is the locus of all points in the plane for which the difference of the distances, the two given points, is constant. So not the sum. For the ellipse here, we had a sum. For ellipse, we had a sum there. Another thing is, see the absolute value of the difference. That's because for some points, the distance to the focus f1 will be greater than the distance to the focus f2, and for some other points, the distance to f1 will be less than the distance to the point f2. So this difference itself could be positive and could be negative. To make things simpler, we say, all right, let's take the absolute value. It doesn't matter whether it's positive or negative. Let's take absolute value. And then when we have some constant 2a. We have some constant 2a. Where does it come into the picture? What does the picture, what does the diagram actually look like? Now remains to be seen. So again, the 2 points are called the foci of the hyperbola, and what it looks like is this. What it looks is this. So for any point on the hyperbola, let me get pen. Supposing we have, for example, the point N. So the distance to F2 and the distance to F1. The difference of these two numbers, of these two distances, has to be the same. Then we have a hyperbola. If the distance from N to F1 minus the distance from N to F2 is constant as N travels in the plane of coordinates, then the path of its travel is actually a hyperbola. We should know this.
Miss, but in hyperbola is one curve, but
Yeah, it's a 12.
but why are we using two curves?
It is one curve. It consists of two parts. It consists of two parts because the difference is the same, only the sign is different. For example, on this branch, on this path, we understand that the distance from N to F1 will be greater than from N to F2. But on this path, in the second branch, the distance to F2 will be greater than the distance to F1. That's one reason why we have two curves. The difference is the same, only the order of subtraction differs. The second case also, remember when we had at the beginning this cone, and we said, okay, conic sections, that is the sections of the cone by some plane. The thing is that all those other planes, those sections were either perfectly horizontal, then we had a circle, then they were slightly perhaps skewed, then we had an ellipse. Now for this, if it's even more skewed, it's parallel to one side, to the side of the cone, then we would have a parabola. But if it's still steeper, now imagine what happens when we try to intersect this cone with a plane that is, for example, vertical. What we see is we would have, okay, we have, the section would go like this, but the plane also cuts the bottom part. So in fact, if I have this vertical plane intersecting that cone, it does cut it twice. We are assuming, of course, that the cone consists of two parts connected at the vertex. The thing is that even this double cone, when we are intersecting with other planes, horizontal, slightly skewed to get an ellipse, even more skewed to get a parabola, they intersect only one part of this double cone, but the hyperbola happens when the plane is steep enough to intersect both. That's why we have this double intersection. We think of the cone as a double object, like as you see, an hourglass.
Okay, thank you, Miss.
Okay, now let's move on. So the standard or canonical equation of a hyperbola, just like with the ellipse, I could, let's say, set the 2 points on the x-axis. I could set the 2 points on the x-axis, put them coordinates, let's say, C0 and minus C0. That's what happens because A is at this point. This is A. This is minus A. This will be C, and this will be minus C. And yes, this will be B. What does B mean? Seemingly nothing. We don't understand what has B got to do with this hyperbola. Why do we need a B? And then there's an interesting situation. If I write down again the equation of the difference, the distance from to F1 minus distance from N to F2 must be equal to 2A, we would have roots, just like with
Miss,
ellipse.
I have a next question, right?
Yeah.
Miss, but ain't the curve at the bottom will be a parabola?
The parabola
Opposite.
will be a bit later on. The parabola will happen if I take this intersecting plane and have it parallel to this line through the vertex of the parabola. If I take this plane, like the vertex of the cone, if I put this plane parallel to this line, then the intersection will be a parabola. In one special case.
Miss, but my question is, but for example, why ain't this will be a parabola? This red at the bottom.
This is a hyperbola. This is a hyperbola because the plane here is steep enough to cut the cone twice. It's simply geometrically something changes. So at some, let's say, while this plane is okay, for the next time I will try to make a new applet for GeoGebra so that I can demonstrate how these things happen. So I will try to make some animation so that I can actually show how and why this happens. It's basically it's best if it can be seen in 3 dimensions. If this demonstration can be seen in 3 dimensions, then it actually becomes probably more clear how and why these things take place. I'll try to put it together for Monday. Okay.
Okay, sure. Thanks.
Mm-hmm. So now let me check the time. Oh, we are all basically close to the end. Actually, it is good that you clarify these things because in order to understand mathematics, one thing is learning the equations, but another thing is understanding how exactly they work. You know, like you can take a clock and see, oh, it tells me a time, but you don't really understand how it works. Only the watchmaker does understand how a clock works. So the standard equation or the canonical equation very similar it looks very similar to the equation of the ellipse. Only instead of plus we have a minus there in the middle. That as you see makes all the difference. So we see that we can still draw the frame 2a times 2b. We can draw this rectangular frame in the picture, this one. I'm now going to mess it up, but doesn't matter because next time we'll start from here anyway, on a clean slate. So in this case, we see that points A and minus A will give us the vertex of the hyperbola, the 2 vertices of the hyperbola, the 2 points, the intersection points with the x-axis. Normally we say B is the intersection of the curve with the y-axis. But in this case, the curve does not intersect the y-axis at all. So we say it's an imaginary intersection. In principle, we could say that the A is the semi-real axis and 2A would be the real axis. Or we can also call it transverse. Real axis or transverse axis. Real because it is really a distance between 2 points. That's why it's real. We can see the distance 2a in the hyperbola. When we have a hyperbola, doesn't matter whether we have a system of coordinates or not. Any hyperbola, we can see the distance between the 2 vertices. Transverse means something that goes across. It goes across the hyperbola intersecting the two parts. Or the B is semi-imaginary. So 2b is the imaginary axis. Imaginary because it does not have a direct connection with the hyperbola. We cannot see this segment except when we actually mark it on the y-axis. For the ellipse, we could see the segment from minus b to b in the ellipse. In the ellipse, we could see from minus a to a. In the hyperbola, we can only see the 2a, only the real axis. The other one, basically, it's not visible. Take away the system of coordinates, and you have no idea what b, where is it? I don't see it. It's imaginary. Conjugate means connected. Conjugate means connected. So transverse half axis means the axis that goes through, and the conjugate is the connected axis. Well, it is connected, of course. It's perpendicular and passes through the midpoint of the real axis. And then the foci are C0 minus C0 on the x-axis. And in principle, then then you see these two dashed lines. They are asymptotes of the hyperbola, and the connection between ABC is, in this case, as you see, the typical Pythagorean connection. We will consider that in greater detail next time. And eccentricity, again, C over A, but in this case, you see the distance C is greater than A. So the eccentricity for a hyperbola is greater than 0. So that's different. And yes, eccentricity of parabola is actually equal to 1. Not greater than 0, but greater than 1. And parabola has eccentricity 1. And then we have these asymptotes, which we can draw through the diagonals of that imaginary rectangle. The imaginary rectangle 2a by 2b, and if we draw the diagonals and continue them behind the points, then we get the two lines that are asymptotes. Asymptote is a line which is approached infinitely close. So the curve itself gets closer and closer and closer to the asymptote. It never intersects it, but it goes closer and closer. As we move away into infinity, the curve goes very close and even closer to this line. But we will repeat this about hyperbola next time. Now it's time for us to finish. Have a very nice weekend.
Yes, but will the asymptote ever intersect? Like even though it's infinity, will it ever intersect?
In this case, never. No. For hyperbola, never. It gets closer and closer and closer. You can imagine going a few kilometers away, and it would still be, well, it might look like it's actually they are actually connected, or they become one, but they don't. The distance will be very, very small, but it will never reach it. All right, people, I will see you. Let's have a well-deserved rest now, and on Monday we will continue with the hyperbola and perhaps also with the parabola.
Miss, when are you planning to have our Unit 3 test?
Unit 3 test, not so soon yet.
Okay.
Because we need Monday to finish, not next week, definitely not next week. We need to finish hyperbola, parabola exercises, and then we have the three-dimensional part of analytical geometry. We will have planes, lines, and intersections. So not before, next week definitely not. The week after that, yes. The week after that.
Okay.
Okay. Goodbye.
Thank you, ma'am.
Thank you, ma'am.
Thanks.
You're welcome.